This is chapter 2, part 4, short videos, kind of going over the solutions to the notes. Remember, the full videos are located below if you need to see those. So, continuing chapter 2, we're going to talk about, well, exponentials. Where else are they used? Well, if you're looking at percent increase, the general formula for an initial investment of $P at an interest rate compounded annually is given here. So, how much is in your account based on the time? You take your principal times 1 plus R, the rate, raised to t. So we have an example here where if you have $100 invested at 5% interest compounded annually, what's the new principal? Well, you have $100, there's your principal. Your rate is 0.05, put that in for R. And then if t is 1, plug it in, you'll have $105. If for 2 years, again, same setup, but use 2 for the years, you have $110.25. But the reason why it's exponential and not linear, notice that the first year we made $5, and then next year we had $5.25. Where that extra 25 cents come from? It's not growing linearly, it's growing exponentially, because the next year we have $105 that we're getting interest from, not just 100. So that's where that extra 25 cents came from. Another example would be if interest is compound interest. So if you had $2,000 in a mutual fund, and you have annual yield of 12.6%, and the interest is not yearly, it's monthly. Notice the formula changes because we add that m. So it's P times 1 plus the rate over m. M is how many times a year, raised to the m times t. So in this case, it's each month, so that's 12 times. So your account, to figure that out, would be 2,000 times 1 plus the rate of 0.126 divided by 12 times a year, times 12t. T we don't know yet. Then, if I want to know to plug in how many years have gone by, you plug in for t. But if I want to know when will it reach 5,000, remember we set it equal to 5,000 because that's the total. That's how much is in the account, and we can solve for that, or we can use the calculator with y1 being the 2,000 times 1.0105 raised to the 12t, and y2 being 5,000. But again, gotta know your window. So practice. You should get 7.31. And also you may notice in the calculator you have this E button. That E button is for the natural base E. Okay? So the E raised to the x, that would be the natural base E. And you see that in the calculator located here. There's ln, which is natural log, log, which is log, and then if I hit second ln, there's that E. So that talks about your ln button, log button, and E. Now, talk a little bit about that natural base. You notice that ln of e is 1. They kind of like reverses of each other. So they kind of cancel each other out. So if you just want to practice a little bit where those buttons are, let's practice. So if I take the calculator out and I do e, clear, start with a nice clean calculator. So if I did second ln, that's where your e is. So e of 2 will give you that number. If I want to do e of negative 0.5, it would give you that number. If I wanted to practice the ln, which is kind of the reverse, natural log, ln of 100, it would give you that number. And if I did the ln of e, second ln, of let's say 3, open parenthesis, close it, open parenthesis, close it, when you ln and e, or vice versa, they kind of cancel each other out, and you're left with a 3. So that's where those are located. And again, sometimes they show up, like for example, from 1994 to 1998, the number of personal computers using the internet grew according to this formula. The formula is n, number in millions, t, time, equals 2.8 e raised to the 0.85 t. So that's used in a formula. So if I wanted to plug that in, I could say 2.8 e raised 0.85 times 2, so after 2 years, we'd expect 15.32 million people having the internet. You could also go to y equals. Let's clear all this out. Clear y1, clear y2. Make sure our plot is off. Going up to hitting enter. We could put in the calculator 2.8 e raised to the 0.85. This time we'll put x. We're not going to put 2. Because x could be any year. So when I go to the table, if I put in 2, it replaces the x, and it gives you the same answer. We can say 3 years or 4 years. So you have multiple ways to kind of practice that, and please do. So here's a problem that's using that formula. Suppose you want to invest $500 in an account that pays 8% interest compounded continuously. And there's a formula for compounded continuously. It uses the E. And the formula would be $500, 8% continuously. So it would be how much is in your account, A, T for time, equals, we're putting $500, there's your principal. E, we know where that is. Interest is 0.08 T. So there's my formula. Let's put that in the calculator. So I go to Y equals 500, second ln for E, 0.08 X, keep it all inside the parenthesis. Now I can plug those values in. So if I go to the table, delete what's there, I can say what happens after 1 year, 2 years, 3 years, 4 years, 5 years, and 10 years. Okay, so if we know the time, we want to find out how much is in the account as it grows continuously, we plug into the formula. But then the next question says, when will I reach 1,000? Your calculator can do this, but you need to understand the problem and understand the window. So when I'm going to use 1,000, it isn't X, it's Y. So I'm going to go to Y, make Y2 1,000. It will draw a line for 1,000. It will have my exponential curve, and where they cross would be my answer. But my window, that's why the table is important. We went from 0 to 10 years. We can count by ones. And remember, we want to see 1,000, and this actually went to like 1,200. So if we go from 0 to maybe 1,200, counting by 200s. Again, we used our data to figure out our window, hit graph, we should see 2 lines. There's my money starting at 500 and growing continuously. There's the $1,000. When will that happen? Second trace, 5 for intersect, enter, enter, enter. It will happen after 8.66 years. You can also solve it algebraically. Remember to get rid of an E, you ln. So there's the work, there's your answer. And then the last thing we'll talk about is logarithmic. Well, logarithmic, then we'll still have logistic to cover. So with logarithmic functions, there's the log button in your calculator. So the way it works, first of all, logarithmic and exponential are just 2 different forms. And if you can go from logarithmic to exponential and then exponential to logarithmic, then you'll realize that they're pretty much the same thing, because log is a little foreign to people, but it's really exponential. So what do I mean by that? Well, if I tell you log base 3 of 9 equals 2, that may look confusing. But if I tell you that 3 squared is 9, you're probably like, yeah, 3 squared is 9. They're the same thing with 2 ways to write it. This would be logarithmic form, this would be exponential form. So how do I convert one into the other? Well, if we're starting with logarithmic, it's 3 log base 3, 9. That 3 is the base, so as an exponential, it's the big number 3, base. The number that it equals would be the exponent, and the number left would be what it equals. So if we can convert one to the other, hopefully we can better understand logs. So for example, if I had 3 equals log base 2 of 8, well, it'd be 2 to the third equals 8, which we know is true. Same thing here. 4 to the 1/2 is 2. Now, if that doesn't make much sense, remember, a half is just like square root. So square root of 4 is 2. And 3 to the 5th equals 3 to the 5th. So if you're able to go from logarithmic to exponential, that will maybe understand logarithmic better. And just to make sure we got it, let's be able to go the other way. So if I want to go from exponential to log, it's 5 squared equals 25. The number with the squared, that's log base 5. 25 equals the exponent, which is 2. Same thing here. Log base 2, 1/2 equals the exponent, -1. Log base a of 2.8 equals the exponent of 1.5. And this one says help, so if you're a little confused now, take your time, study. Log base h of LP equals E. So again, to go back from logarithmic to exponential, hopefully better explains logarithmic. Now you do know that in your calculator you have the log button, but understand when you use that log button, it's understood that the base is 10. So if I did log of 1,000 in my calculator, clear, log, there's the button to the left of 7, of 1,000, enters 3. Now why is it 3? Well, if we converted, that's a 10, Remember, it's understood to be a 10 if it's not there. 10 to the third is 1,000. 10 to the third is 1,000. That's where the 3 comes from. So if I wanted to practice and do 6.5 and 256, log 6.5 log 256, we know where the number is. We could practice that. You get 0.813, 2.41. But what if it wasn't log base 10? What if it was a different? Well, we have a formula for that. So if it's not base 10, the calculator can do it, but a quick way is to do the change of base formula. So we would say log of 9. So if I had log base 11, 9, I could say log of 9 divided by log of 11, and I'd get the answer. So to practice that, go to the calculator. So if there's a number different than 10, we would do log of 9 divided by log of 11, using the change of base formula, and you get your answer. Same thing here. If I had log base 3.2, 1.4 over 3.4, I would say log of the 1.42 divided by 3.4 divided by log of 3.2, and you get your answer. Okay, so that's a good formula to use, especially when we're graphing, which is the last thing we're going to do. So a logarithmic function looks like this. It goes up and kind of flattens out. Goes up and flattens out. And it's log base b x plus c. So again, we can use the change of base formula. And what we're going to do is we're going to practice. So if I had log base 2 of x and I wanted to plug in values, I would rewrite it as log of x divided by log of 2. Then I can plug in those numbers. So if I go to the calculator, it would be go to y equals, clear what's in there. There's a way to do that, but I'm going to show you how to use the change of base formula. But log base 2 of x, I would do log of x divided by log of 2 using the change of base formula. And I'm going to plug in those numbers. So if I go to second table and I plug in 1/8, 1/4, 1/8, 1/4, 1/2, 1, 2, 4, 8. You get your answers. Now, if I wanted to graph it, we can use this window here based on the data. Let's say -2 to 10, counting by ones, and -5 to 5, counting by ones. Hit graph. You can see that shape and where it comes from. Okay? And then we have an example here, but this is kind of going back to the exponential one, so you can kind of look over that example. And let's conclude.